All right, we're coming back to the political ecology of corona, and we're moving into the regression models. The last video went about 14 minutes. I don't like to keep them that long. I hope to finish this one off in about 10 minutes. And here we go. We're going to go back to GeoDot, where we left off. And we'd have zounds of scatter plots showing us the bivariate relationships. I didn't talk about the distribution of the x variables here and the distribution of corona here, which we see is not normally distributed. That said, remember, the assumption for linear models isn't that the y is normally distributed. It is that y conditioned on x, meaning the errors are normally distributed. So let's bounce back over to our main menu here, and we're going to go to create a weights, because to do spatial regression and to calculate spatial dependence, we have to create a weights matrix. And so we're going to create one, and we're going to select the ID variable, and we'll use FID in queen contiguity. It already exists because I've been playing with this, and it tells us that there's one neighborless observation. We know we have some islands that don't touch anything, and we maybe should fix that, individually edit the neighbors, etc., but we're not going to do that right now. A neighbors matrix just is a matrix that for each observation says which other observations in queen contiguity touch me. And I say OK, and it was successfully created, and I'm going to do close, and we could look at the connectivity map. And so if I come over here and I click, this shows who the neighbors are, and you see there's some little bitty problems here in terms of some of these don't have any neighbors, right? And there's some that should have neighbors, but for whatever reason in the way we'll have to fix some of the polygons to fix those neighbors. But we're going to charge ahead here before we fix them, because we're just sort of in the early stages of this, and I'd like to get going. So we're going to go to a regression, and we're going to select our weights file. But the first thing we need to do is go and put our Corona 516. Yes, epidemiologist. Oops, I missed badly. One of the things about this is when you use a dependent variable, it throws it down to the bottom when you remove it. So we're going to use Corona 516. That's the number of cases from the New York Health Department put on their GitHub site. And I'd like to put in some variables we think are important. We think population density is important from the spread of a disease. If you're closer, you can get it more easily. So we're going to put in nursing beds. And notice how I select it and then put it over into the covariates. Buses, railroads, subways, trees, all of those. We're not going to put tests in. Tests messes up a few too many things. We're going to come down here and do our percent Black or African American. Percent Hispanic. Clinton. Cruz, which we saw. And Trump. And we're going to do the total number of people in New York housing authorities. We're going to add our stairwells, and I think that gives us everything that we wanted to do that looked like it was worth adding from our bivariates. Sometimes you don't want to, you want to add other things that should be, other variables that should be important. But from what we looked at, we'll go with this, and it's a good start, and we can play with our models. I'm going to select the weights file, and this will tell us whether we have spatial dependence or not. Then we're going to click Run. Don't close this or you lose your analysis. And so we slide down, and the spatial dependence we see, the Moran's I is significant, Lagrange is significant. All of these spatial, the ones most people know is Moran's I, all of these are saying that there is probably a high chance that things are spatially aggregated in terms of where they occur for coronavirus. We already knew that looking at the map, but this confirms it. We haven't corrected for it yet, but population density is positive and highly significant. Nursing beds are positive and highly significant, meaning the higher the population density, the more corona. The more nursing beds, the more corona. The more bus stops, the more corona. LIIR turns out to be negative, but no difference than zero statistically. Same with the buses. Subways are positive and significant. Well, okay, so it's getting tracked in the underground. Trees are positive and significant. So hanging out in parks and being around trees, trapping your dog, it's a social aggregating factor. That was significant. There may be some aerosol dynamics at play, but I have no idea. Percent black or African American, positive and significant. That shouldn't be surprising. Percent Hispanic, positive and significant. Clinton voters, positive and significant. Cruz voters, positive and significant. Trump voters, positive and significant. So you're saying, well, that seems a little odd. But remember, these are primaries, so may have just been more densely populated areas that the candidates won there in greater numbers, greater percentages. But this would require some digging into in some greater ways. And then our New York City Housing Authority population was negative and not significant, and the stairways was negative and not significant when we started controlling for other things. How well does this model fit? Has an R-square of about 0.69, so that's not bad. For economists and political scientists, that's very, very good. For chemists, it's an F on your paper. So this is a pretty good shot, but we know there's that spatial dependence, and maybe the fact that everything is just spatially aggregated means that we're capturing many things that are spatially aggregated at the same time. So one of the nice things about GeoDAS, it allows us to do this relatively easily. We can do it in R and a number of other places, and I like doing it in R, but setting up your spatial weights matrix in R is really flexible and therefore potentially really confusing. So we're going to go to a spatial lag, and in the spatial lag model, what it does is it takes the neighbors, the corona infection in the neighbors, and puts that in as an explanatory variable. And then in a maximum likelihood format finds the best set of coefficients that help us understand this. So we're going to go ahead and run that. And we bounce over here, and we see our R-square went up a bit, not hugely, but a bit. And we see that here, that's our corona weighted, the lagged corona weighted, and we see it is highly significant and a good explanatory variable. Population density remains positive and significant, as do nursing beds. Buses are not. The railroad is not, as before. Subways still are positive and significant. Trees are still positive and significant. Percent African American, percent Hispanic, also still positive and significant. Clinton, Cruz, and Trump, well, Trump is no longer significant. And our housing authority variables remain the same. So that is comforting that our OLS, our ordinary least squares regressors, and our weighted regression model, our spatial lag model, gave us very, very similar outcomes in terms of sign and significance. We're going to run one more model, which is the spatial error model. This says we don't think there's a relationship between the coronavirus and nearby coronavirus, but we think maybe the errors are spatially aggregated. It's another approach to doing it, and I'll put some readings on the website to do this. So I'm going to run that again, and we come up and we see the lambda is that variable down here, right? This is our correction for our spatial error being related, and the z-value is very high and the probability is very high. We go back up and look at our R-square, even a little bit higher in the spatial error model, and let's see what popped out there. Population density is still positive and significant. Nursing beds, now buses are, the LIRR is still not. Subways are, Trees are still positive and highly significant. Black or African American, Hispanic percentages, Clinton again, Cruz again, and Trump is not. We see nothing out of our New York City Housing Authority folks doing a great job keeping their buildings clean and getting their people hand sanitizer. Let's give a shout out to those folks. And that's it. That's sort of it. We could do an awful lot more here in terms of doing further analysis and further assessment of whether these parameters are good or driven by outliers or other things like that. But here we've done it. We've done a political ecology. We've got the politics in there. We have some ecosystem stuff in there in terms of trees and hallways and buses and aggregation areas. I haven't put the age in there. It's in the data set. Feel free to play with it at your heart's content. You are welcome to use this. I would error check it first if I were you. I always think it's a good idea to error check other people's data, even though I don't always do it. Thanks. I hope you enjoyed.